Okay, ladies and gentlemen, so this video is going to focus on solving problems involving exponential growth and decay. So let me break this down for you a little bit. Growth is those graphs that we were looking at that are exponential, that are increasing. Decay are those graphs that we were looking at that are, oh, what did I just do? That are decreasing. There we go. Okay, so this is nothing new. We're just looking at the real world connections now. And we're looking at writing the actual equations that go with these real world connections to think more about growth and decay exponentially. So, what kind of situations could be examples of real world exponential growth or decay? Anybody have any ideas? First things that come to mind for me are things like population growth. That's this little Timmy over here. The other thing that can grow exponentially or decay exponentially, lots of times finances have a lot to do with growth and decay. Interest. And then the last super common one is science, bacteria. Bacteria has an awesome track record of exponential growth. Okay, so that's why people get sick so easily, is because it's growing pretty rapidly. All right, so let's look at an example. This example, we need first to understand the formula for exponential growth or decay. Now, remember, we've been looking at exponential as just y equals a times b to the x. To the x. Now, this is very similar. There's just one small thing we're dealing with here. So we got y equals a, and a in this case is the initial amount, times, and our b is 1 plus r, and r is the rate of change expressed as a decimal. So, for example, a rate of change could be 30%, but expressed as a decimal would be 0.3. Okay, so that's the rate of change, and then we add 1 because it's growth. And then we've got the exponent, in this case is t, representing time. Okay, so that formula you're going to want to write down and you're going to have handy. So this first example is about population. It says in 2008, the town of Flat Creek had a population of about 280,000 and a growth rate of 0.85% per year. Write an equation to represent the population of Flat Creek since 2008. So 2008 is going to be our year 0. Okay, so we've got y equals a, the initial amount was 280,000, times 1 plus r. Remember, r is the rate of change written as a decimal. So this is a percent. How do you make a percent a decimal? Well, looking at this example, we are dividing. Wow, that's a really ugly division sign, friends. Dividing by 100. Okay? So I'm going to move the decimal place 2 places to the left. So that gives me 0.012085. That's a really, really small rate of change. This population is not growing super fast. To the t. And remember, t is the amount of time. Okay, so in part B here, it's asking us to use the equation we wrote to find out the population of Flat Creek in the year 2018. So remember, our equation is since 2008, so that's our year 0. So our t that we're going to plug in is going to be 10, because it's 10 years after. After typing that whole expression into my calculator using 10 instead of t, I get an answer of 304,731.29. Now I'm talking about population, I'm talking about people, so what do you think I should round to? People don't come in halves, so I should round to the nearest whole number without rounding up. Okay? So that's the number of people in this town. Now I'm going to check my answer to make sure that makes sense. Time has passed, so it should increase. Did it increase? Yes. A reasonable amount? Seems like it. Okay, let's try another example. A population in 2008, Kyoto School District had a student population of about 4,500 students and a growth rate of about 0.15% per year. Write an equation to represent the student population of the Kyoto School District since the year 2008. Alright, so they give us a lot of examples here. I know it's not this one because I need the initial amount. I know it's not this one because it's missing the 1. I know it's not this one because it doesn't have an exponent of t, so it's going to be that example there. Now they're asking us to actually determine how many students there are going to be. So since 2008, we're now in 2014, so I'm going to use a t of 6. So when I type that in, it tells me they're going to be 4,540.6 students. So correct answer, without rounding up, remember, we're not counting halves of students. Correct answer would be C. Alright, let's talk about exponential decay. Exponential decay is very similar to growth. You'll notice that A is still the initial amount, T is still time, and R is still the rate expressed as a decimal. The only difference here, ladies and gentlemen, is that we are subtracting from 1. So let me explain a little bit more about this adding 1, subtracting 1. Okay, with growth, you're adding 1. Why? Because you're growing 100%, so all of the population you currently have, plus some more. In decay, we want the 100% of the population minus decaying, going down a certain rate. Okay, so you're taking that whole population, you're taking away a part. So let's take a look here. It says, during an economic recession, a charitable organization found that its donations dropped by 1.1% per year. Before the recession, its donations were $390,000. Write an equation to represent the charity's donations since the beginning of the recession. So it's going to be y equals A, the initial amount, 390,000, 1 minus our rate, written as a decimal, which would be 0.01211. Alright, 0.011 to the t power. Now I'm going to simplify that. I'm going to do 1 minus 0.011, and that gives me my rate that I'm going to use. 390,000 times 9.989 to the t power. Alright, so now they want to have me estimate the amount of donations 5 years after the start of the recession. So t is going to be 5. So I type that into my calculator, and that'll give me $369,016.737. Okay, now I need a round here. We're talking about dollars. So you have 2 decimals after, or 2 places after the decimal. And so since this is bigger than 5, I'm going to erase the 7 and the 3, and I'm going to round up then. That's going to be $0.74. Alright, let's try another example. A charitable organization found that the value of its clothing donations dropped by 2.5% per year. Before this downturn in donations, the organization received clothing valued at $24,000. Write an equation to represent the value of charity's donations since the beginning of the downturn. Alright, so I know it's not this one because it's missing the initial amount. I know it's not this one because 0.975 and a 1, that'd be growth. All right, and I know it's not this one because there's no t, so we're looking at B here. The initial amount, 1 minus 0.025 will give me 0.975 to the t. All right, let's keep going. All right, so they want to know 3 years after the start of the downturn. So we're going to use that same equation that we wrote. Y equals 24,000 times 0.975 to the third power, because 3 is the number of years. And that's going to give us 22,244, which 0.625. All right, so they're not using the nicest rounding here. If I were doing this test, I would write my final answer as $22,244.63, but they use the word about, so in multiple choice, I'm going to choose C. Okay. So homework tonight, you're doing 4 problems. Now, I want to help you with this a little bit. How do you know when you're supposed to add one or when you're supposed to subtract one? You need to look for key words that tell you whether it's growing or decreasing, like the word increase, decline, increase, and losing value. So those should help you to be able to write your equations and to work them out. Good luck.